So it's great to be here, and I appreciate the opportunity to present our work. Today I'm going to be discussing one of the areas that we're working on here at Duke on solution processing of thin film solar cells. And I should mention that this is an area I joined Duke about 9 months ago. So much of the science that I'll be talking about, how to get this to move down. There we go. Much of the science that I'll be talking about actually took place at IBM, and I will acknowledge and thank the very talented team of researchers that I worked with at IBM over the years, and also joint development partners. But more importantly, or equally importantly, I'd like to thank my new team who's starting to set up some of the projects that I'll mention as well during the presentation. So, as with everyone working in the area of photovoltaics, we're targeting low-cost, high-efficiency photovoltaic devices. In the particular case of our lab, we're focused on thin-film PV as opposed to crystalline silicon. This is one aspect of trying to reduce cost. We're also focused on using abundant or readily available elements. This is so that if we develop, or when we develop, an appropriate technology, it can be scaled to very large production levels. And finally, we're interested in solution-based deposition. And again, this is an aspect of trying to reduce cost. And so today I'm just going to briefly describe two areas that we're interested in. One is CZTS, copper zinc tin sulfide selenide, and the other are these perovskite absorbers that are currently generating a lot of excitement. So to start off with, I think most people are aware of the explosion of interest in photovoltaics. If we look at thin film PV in particular, these are the top 3 bars on this graph here showing the market share of the different technologies that are around. All the rest of this is crystalline silicon, and so thin film PV accounts for about 10% of the market, and it has over the last 5 years and is projected to continue at this level. But you can see that the mix of technologies has shifted from amorphous silicon to the chalcogenide-based, the SIGs, and the cadmium telluride-based photovoltaic systems. We can also look at the overall growth in thin film PV. It's grown with the market for photovoltaics overall. And it's gone from around 2 gigawatts per year up to around 4.5 projected for 2015. And over this time, the geographic distribution has shifted from implementation in Europe primarily to the US and Japan. And so currently, SIGs, copper indium gallium sulfide selenide, and cadmium telluride are dominating the growth. But one of the questions we're asking here is are there thin film technologies that can shift this market share or shift the technology away from crystalline silicon toward thin film in an effort to try and enable PV to reach grid parity sooner? And so with this, it's useful to start looking at the current technologies, so cadmium telluride and SIGs. These are both technologies that have over 1 gigawatt of cumulative production. A number of advantages, including that they're direct bandgap semiconductors, so that the absorbers can be made very thin. The grain boundaries are benign with respect to recombination of the photogenerated carriers. And this is important so that we can use polycrystalline films instead of needing to deposit single crystal layers. Again, an effort to reduce cost. The technologies are compatible with monolithic integration, so we don't need to pick and place silicon wafers. We can basically process across large glass plates, again, reducing cost. And finally, the thin film nature and polycrystalline nature make it compatible with flexible substrates, and this not only opens up opportunities for new form factors, such as wearable, ultra-lightweight, foldable, building integrated PV, but also opens up the opportunity for roll-to-roll processing, such as what Jeff was mentioning. So these are very compelling advantages, but there are also some drawbacks. Namely, cadmium telluride involves cadmium, which is a heavy metal, and both technologies use elements that are rare in the Earth's crust, tellurium and indium. And this brings up questions about the scalability. And so for this reason, we're interested in this other compound, CZTS, copper zinc tin sulfide selenide, in which the expensive and relatively rare indium and gallium are replaced by more abundant and lower cost zinc and tin. And this is a technology that started back in 1988 with the first demonstration of a photovoltaic effect. In 1996, the first thin-film devices were made, which demonstrated efficiencies less than 1%. Over the next 12 years, efficiencies increased by about an order of magnitude, and this was entirely done using vacuum-based deposition approaches like evaporation and sputtering. The basic device structure is fairly typical in the thin-film field. We can make it on glass or a variety of other substrates. We have a conducting back contact. We put down the CCTS. We complete the PN junction by putting down an N-type material, such as cad sulfide or indium sulfide or zinc oxysulfide. And then we have a top contact, a transparent contact of ITO and intrinsic zinc oxide. And the sun impinges on this device from the top. You can see that the CZTS layer is the dominant or the thickest layer in this device, and the crystalline nature of this layer and the electronic properties of this layer are of critical importance in terms of dictating how efficient this device is going to be. And so we'll focus on this layer for much of this presentation. The other aspect of reducing costs, besides going to thin film, is solution processing. We're interested in solution processing because it doesn't require evacuating a large chamber. There's no need for high temperatures during the deposition. We don't have to evaporate. We don't have evaporation sources that require relatively large energy input. There's also the prospects of very high throughput. And the process is very simple as well. We just dissolve the materials. We can deposit it onto a substrate using some rather low-tech approaches, and then heat treat it to evaporate the solvent, perhaps decompose a precursor, and ultimately induce grain growth to get the final film. And the question we encountered was, how can we get the CZTS into solution? And so one approach we used was the solvent hydrazine, N2H4, which enables dissolving many of the metal chalcogenides in sulfur and selenium, and also cleanly decomposes, leaving a film that's of good electronic quality. Of course, it does have some issues, its combustibility and toxicity, that need to be taken into account. But with this in mind, our process simply involved dissolving copper, tin, sulfur, and selenium in hydrazine. And then, since zinc does not readily dissolve in hydrazine, we added it as an elemental powder, which reacts in situ to form these zinc chalcogenide nanoparticles. And then, if we take this slurry, we can process it into thin film form, heat it to temperatures above 550 degrees C, and we get the desired CZTS film. And using this approach, we were able to increase the efficiency of these CZTS devices by about 40% over what had previously been achieved. So this was quite exciting. And in addition, if we look at these films, they weren't really that pretty. There was a lot of small grain material at the back, which can act as a recombination zone in the device and hurt the device performance. And so by optimizing our deposition approach to get rid of some of the smaller grain materials, we were then able to push the efficiencies, the first examples, above 10% performance. And this was done almost entirely by improving the short circuit current and fill factor of the device. The open circuit voltage remained roughly the same. So we can compare now our current, at the time, record device with the Shockley-Kaiser limit, which is the fundamental limit of a single junction solar cell at that particular band gap value. And we can see that of the three parameters that dictate the efficiency, the short circuit current and the fill factor are not that far from the SQ limit, whereas the open circuit voltage is suffering quite a bit. And so to track how we're doing in open circuit voltage, we can define an open circuit voltage deficit as the difference between the band gap and the open circuit voltage. And for a good device, we want this to be less than 0.5. For the best SIGS devices in gallium arsenide, this is around 0.4. Whereas in our CZTS devices, this is greater than 0.6 and generally greater than 0.7. So with this in mind, we thought, well, maybe it has something to do with our deposition approach. We are using nanoparticles. We know particles like to aggregate, and so we developed a new chemistry where we started with a zinc salt, which coordinates the zinc, enabling it to go into solution, thereby enabling, hopefully, more homogeneous films. And if we look at these films, the solution process films are much shinier, they're smoother than the slurry process films, and indeed they're also more electronically homogeneous. So these are light beam induced current studies where two different wavelengths, and you could see from the slurry process and the solution process devices that indeed these solution process devices look more uniform. And so by using this approach, we were able to then generate what's now the world record for these devices at 12.6% power conversion efficiency, and get the highest, or the lowest, VOC deficit that we've been able to achieve so far for these devices at 0.62 volts. And more recently, we've been able to decrease this to below 0.6 volts for the first time. While VOC's improved, still this is one of the biggest issues, trying to get this still lower. And it opens the question of where this VOC deficit is coming from. And one of the areas we think is most important involves the messiness of these materials. There are a lot of different elements, and there are opportunities for disorder which can introduce band gap fluctuations or electrostatic potential fluctuations. The band gap fluctuations come from non-uniform composition, such as, for example, what I described with that nanoparticle aggregation. And then we have electrostatic potential fluctuations, which are due to charge defects. Regardless, these fluctuations in the band edges induce a reduction of the effective band gap that reduces the achievable open circuit voltage. And so we understand where the band gap fluctuations can come from. What about the charge defects? Density functional theory can be used to predict the formation energy of defects and also the energetic position of these defects within the band gap. And we can immediately see that there are a number of low energy formation defects, meaning that they'd like to form. And in particular, these copper on zinc defects, these anti-site defects, are very prevalent. They've got a negative formation energy, and in fact, if you look at neutron diffraction or resonant X-ray diffraction, you can distinguish how many there are in the sample. And it turns out to be on the order of tens of percent, 20, 30%. So this is macroscopic disorder in the sample. And we can also look at the energetic position of these defects and see that they're moderately deep in the band gap, but if we get a sufficient concentration of these defects, these energy levels can broaden out and merge with the valence band. If we look at the experimental data, we can see evidence for band tailing. If we look at the quantum efficiency, basically this long wavelength tail corresponds to the band gap cutoff, and it's proportional to the absorption coefficient, which in turn is proportional to the density of states. So tailing in the quantum efficiency corresponds to tailing in the density of states. And if we compare the commercial SIGS type devices to our CZTS, we see a much shallower cutoff at the band gap. And likewise, if we look at photoluminescence, the photoluminescence peaks are broader and shifted further from the band gap value. And these are both consistent with band tailing. We can also look at time-resolved photoluminescence to get an idea of lifetimes, minority carrier lifetimes, and see that SIGS and CZTS are roughly the same at room temperature. But at low temperature, there are dramatic differences. The lifetime for SIGS stays about the same, whereas for CZTS, it increases by several orders of magnitude. And so we take this as evidence of electrostatic potential fluctuations in this material, namely, at low temperature, when we photoexcite electrons and holes, they populate pockets that are physically separated, and therefore reducing the probability of recombination. And we propose that these fluctuations are responsible for the bulk of the VOC deficit issue. And so this is an issue for moving forward. I think at this point, we've had very good progress in trying to improve the efficiency in CZTS, continuing to push this forward. Most of the progress has come in short circuit current and fill factor. We've more recently made some progress in open circuit voltage. In order to push this technology further, the critical thing is to be able to understand and control this anti-site disorder and band tailing that exists in the material. And currently here at Duke, we have a program that is now seed funded by the Duke Energy Initiative, which combines theoretical and experimental capabilities to try and use what we've learned from CZTS to design and implement new materials that will have reduced anti-site disorder and hopefully improved properties. So I'd like to briefly mention one other exciting area of solution process absorbers, and this relates to perovskites. Back in the 1990s, I was looking at trying to find systems that exhibited solution processability at ambient temperature, while at the same time offering tunable semiconducting properties. And we were looking at the metal halide-based systems, which at the time were unusual to look at for semiconductors. Most are insulators, but came across this family of tin, germanium, and lead halides, which had this very high degree of tunability in terms of their semiconducting properties, as well as solution processability. And because of this, we were able to demonstrate them in LEDs, thin film transistors, and a variety of other applications. However, it was more recent that interest started to be generated for photovoltaic applications, and a great deal of excitement has occurred because of the rapid rise in efficiency. Started out around 3% in 2009 and is now up above 20%. This is already out of date. But you'll notice that the open circuit voltage deficit is already very low, attesting to the high quality of the semiconducting material. And this high quality of the material is attributed to the direct band gap nature of the semiconductor, the P-like character of the band edges, valence band and conduction band, which gives rise to very high absorption, which in turn enables ultra-thin absorbers, meaning that the photo-generated carriers do not need to move very far. And likewise, because of the strong SP coupling at the band edges, we get both electrons and holes that have small effective masses, which makes it easier to collect the carriers once they're generated. And likewise, we have very little recombination in the device. The dominant defects are shallow. Also, the grain boundaries turn out to be benign with respect to recombination. And this accounts for the very high open circuit voltage, voltages in these devices. And so these materials are very promising. However, they do have some challenges, and we currently have two programs that have been initiated here at Duke. One is funded by the Department of Energy, and it's focused on continuing to try and push to higher efficiency, but at the same time replacing the heavy metal lead with other less toxic alternatives, and also to address the issue of the moisture and air sensitivity of the current generation of perovskites. And like for the other project that I mentioned, one of the hallmarks of our programs is to try and combine theory/computation with the full range of other activities: materials development, device integration, and device analysis. This was one of the things at IBM that was set up, trying to create this holistic program, and that's also something that I'd like to do here at Duke. In addition, we've got a program with Jay Liu's group in chemistry to use this nanoengineering to tailor and understand interfaces in these devices. And another program, which Adrian may mention later, but working on an innovative approach for depositing the perovskites based on resonant infrared matrix-assisted pulse laser evaporation. This is exciting because it enables deposition of organic and inorganic materials regardless of finding a compatible solvent. And so, to finish up, I hope I've shown some of the ways, or these two systems, where not only can solution processing be used to create lower costs, but also some of the highest performing devices in the field. And in addition, I think it provides opportunities for interesting science and engineering. And so with that, I'd like to thank you for your attention.
All right, we have about 10 minutes available for questions for David. Neil.
On the perovskites, you said you're at 25%. So what's the theoretical maximum you can get to with that?
First of all, we're not at 25%,
Oh,
but 20.8 is the last I've heard. 20.1 is the highest for certified. But in terms of theoretical efficiency for a single junction solar cell, it's on the order of 30%. That being said, one of the applications that's being looked at for these materials in the near term is related to creating tandem solar cells. And the reason that's exciting is twofold. One is, well, if you have these existing silicon, I mean, silicon is so dominant, if you have a very low-cost way of adding value to those solar cells by boosting their performance by a few percent, that's attractive. The other thing is that often when you're making tandems, one of the problems is that the solar cell on the bottom has a low thermal budget. You can't heat it above, say, 300 degrees. And many of these solar cell technologies require high temperatures to process. The perovskites can be processed at room temperature, and so it opens up opportunities for creating tandems in that way as well.
Would you get to a point where you abandon one and go full scale onto the other?
One and the other?
In terms of the perovskites, or you know.
I am personally a new materials person, and I like to explore new materials. So I suspect that at this point I will continue to pursue both aspects of the technology, both the chalcogenides and the metal halides. Obviously, if one takes off in a meteoritic type of way, you know, we could go in that direction.
Well, and of course, we live by funding too, right?
Exactly.
So.
And I have commitments, in both cases I have commitments for...
So you get the money from us.
Exactly, yes.
So the three factors you mentioned in the fill volume, are they completely independent? So if you increase the fill volume, will it have an effect on the open voltage?
Yes. So actually they're not independent necessarily. So for example, of the three factors, if we increase the open circuit voltage, we also will increase the fill factor. So those two are connected. And likewise, the short circuit current also has a logarithmic connection to the open circuit voltage. So they're not completely independent. Any other questions?
I actually have one question. So when you talk about tandems, those are stacked solar cells essentially, right? Can you actually think about stacking the perovskites because they have a tunable band gap? Could you create a stack of perovskites that basically cover efficiently the spectrum?
Yes, yeah, you could, and people are interested in doing that. There are two types of structures that are of interest for making tandems. One is a mechanically stacked tandem, where it's actually a 4-terminal device. Mm-hmm. The other is an integrated device, where it's a 2-terminal device. In the 2-terminal device, you have the added complication of having to match the currents.
Right.
But in any case, one of the problems with creating the integrated device is that you have to be able to put down the perovskite in a way that doesn't dissolve.
The previous perovskite.
Yes, exactly. And so, for example, one can think about doing that by evaporative approaches. Mm-hmm. So it is possible to put these down from the vapor phase as well. There are also people working on ALD as a way of putting it down.
Or a barrier layer that might lie between the two perovskites.
Exactly. Yeah, these are tremendously diverse materials. The 3-dimensional perovskites that are primary interest now are just the tip of an iceberg. I mean, if you look at the layered structures, then there's possibilities of polymerizing the organic layer, which can make it insoluble. And so we have a whole bunch of ideas that we'd like to work on to try and implement the broader family of, bring the broader family of materials into play, and apply them not just for PV, but also for LEDs, energy storage, a variety of other applications. So, but the issue of lead, the issue of stability, the issue of hysteresis, these are not as simple as they appear.
All right, well, let's thank David one more time.